G'day, in this video we're going to have a look at the standard model of matter. This video covers dot point 8.5.1 and 2. Inquiry question 5 is all about digging deeper into our scientific understanding of matter and acknowledging that even though we have some basic principles that help to explain all sorts of phenomena, the model itself is still incomplete. In order to appreciate that, we need to dig a little bit deeper than we already have. We have an understanding of protons, neutrons, and electrons, but there are other subatomic particles that exist, and protons and neutrons themselves are not fundamental particles. And so in the second half of the 1900s, there was a lot of work to develop our understanding beyond the basics that we've already learnt about in this module. And through a collection of work from countless scientists across the world, we now today are able to work within the parameters of the standard model. And in this video, we're going to begin to look at some of the elements of that model and how they build on our fundamental understanding of matter. So today, what we're going to be doing is first establishing a common understanding of what it is to be a fundamental particle. We're then going to talk through some of the work of Murray Gell-Mann, a famous theoretical physicist whose work provided a lot of foundational building blocks for the development of the standard model itself. We're then also going to explore how protons and neutrons were determined to be not fundamental. And then at the end, I'm going to be giving you some building blocks in understanding the standard model of matter. It's important to understand that a lot of the content that you're going to be looking at in this video, as well as when we go a little bit further in class, is in a lot of ways beyond the scope of how you're probably going to be assessed in this course. However, to understand a lot of the basics, which are definitely accessible in the course, we need to have quite a broad understanding of the concept in its entirety. And so while there are lots of new concepts that are being introduced, lots of new terminology, they all come together to paint quite a broad picture. And if we are able to understand the basics of that picture, then understanding the syllabus content is going to be a lot more achievable. So let's start first with understanding fundamental particles. Essentially, by definition, these are as basic as particles can get. They're indivisible. They're not made up of smaller parts. These particles are effectively assumed to be uniform. Originally, atoms were thought to be the fundamental particle. We've talked about this with things like the Dalton model before. However, as our understanding of the atom deepened, we discovered things like protons, neutrons, and electrons. And that meant that our understanding of the atom as a fundamental particle was now incorrect. And so the model changed so that the protons, neutrons, and electrons, the building blocks of the atom, were considered to be fundamental instead. However, as you'll see in the rest of this video, there was a lot of work beyond the discovery of the proton, neutron, and electron that we looked at in this model already. And what we found was that there were other particles that existed as well. So that begs a question. What are these particles? Why did they exist? Which were fundamental and which were what we call composite? Composite meaning that they are made from multiple particles. So for example, the atom itself is a composite particle because it's made of 3 different particles. We'll see too that the neutrons and protons themselves are also composite particles because they're made from smaller constituents as well. In this bottom timeline, you will see that there are the discoveries of various types of particles, some fundamental, most of them composite. And in this top timeline, you're going to see that there is a bunch of particles which are here, all of which are outlining discoveries of fundamental particles. In order for a particle to be a newly discovered particle, essentially they had to be distinguishable from other particles. And what that means is they need to have different sets of properties. In this topic, the main sets of properties that we will refer to are mass, charge, spin, and strange. Mass and charge will be quite familiar with. Spin has been talked about very briefly in some contexts, but is still probably quite unfamiliar. And strange is probably the first time you've heard about this one before. I want to make it really clear that in the context of this course, we don't have to have an in-depth understanding of what spin and strange actually are. All we need to know is that these are measurable characteristics of particles, that they are quantitative values that can be given for these, and that these values could be positive or negative. And therefore, if a particle has different sets of spin and strange, then that means that they are different from other types of particles. I'll come back to these terms a little bit later, but baryons and mesons are groups of particles based on some of these properties. You'll notice in the table that these baryons all have a spin of half, and the mesons have a spin of 0. This is because baryons have spins of half integer values, so 1/2, -1/2, 3/2, something like that, whereas mesons have whole number integer values. So they have spins of 0, 1, -1, 2, -2, etc. So automatically, these three baryons are going to be considered different and grouped differently to the mesons simply due to their spin. But within our set of baryons or our set of mesons, things like charge and strangeness will then further distinguish these particles from each other. So going back to this timeline here, we were discovering all of these particles, and they had different sets of combinations of properties, different spins, different charges, different strangeness. Colloquially, all of these particles in the 1960s were referred to as the particle zoo. We had all of these particles. They needed to be classified similar to the animals that exist in a zoo, but organizing them in any meaningful way was quite difficult. And so Murray Gell-Mann attempted to relate all of these particles by their charge, spin, and strange in a way that geometrically and mathematically made sense. What he was able to do was plot all the particles in geometric patterns by first grouping each of the particles by their spin and then plotting their charge against their strangeness. However, this is not your regular Cartesian style plane. Instead, the charge was plotted at a 45-degree angle. And so when he did this, it led to these amazing geometric patterns, some hexagons as well as a bit larger of a triangle. Should be also noted that at the time of Gell-Mann's work, the spin 3 on 2 plot looked like the zone drawn in blue. The omega minus particle was not yet discovered. However, using this model and the principles of geometry, Gell-Mann predicted the existence of a particle that had spin 3 on 2, a strangeness of -3, and a charge of -1. He was later proven to be correct on this. As a part of his work, Gell-Mann predicted that these particles were also composite, meaning that they were built from fundamental particles that had their own sets of properties. And this gave reason for why you could have all of these particles with different sets of properties. They were built from different foundations, and in different combinations, this would lead to differing amounts of charge, differing amounts of strange, and differing amounts of spin, depending on their composition. These fundamental particles came to be known as quarks. As an example, protons and neutrons, which we're quite familiar with, are made from what we call up and down quarks. Up quarks have a charge of +2/3, whereas down have a charge of -1/3. They both have spins of either half or -half, and strange of 0. Something key to note, and we'll come back to this as we go through our content today, but the Pauli exclusion principle also applies here, just like it did for electrons sitting in orbitals. Essentially, when we form a composite particle out of quarks, no two quarks can possess identical quantum numbers. For example, I could not have a particle that was composed of two up quarks, both with the same spin. You would have to have one up quark have spin half and one up quark have spin -half. This again works quite similarly to how we looked at electrons in orbitals. Essentially, if two electrons existed in one single orbital, they had to have positive and negative spins respectively. So let's apply some of these ideas to build some protons and neutrons. Again, we have to remember that the Pauli exclusion principle applies when forming composite particles from quarks. Let's start with the proton. As identified before, protons are built from up and down quarks, and they have charge of 2/3 and -1/3 respectively. Now, there is only one way to combine these quarks together and form a particle which has a charge of +1, the charge of a proton. And this is achieved by combining two up quarks and one down quark. Two charges of 2/3 plus a charge of -1/3 gives us in total a charge of +1. Now, all three of these quarks are going to have a strange of 0, which means based on charge and strange, these two up particles currently have identical sets of quantum numbers. The only remaining quantum number left is spin, and these must be unique to satisfy the Pauli exclusion principle. What this means is one is going to have a spin of half and the other is going to have a spin of -1/2. Now, as it stands, these two spins combined together gives an overall spin of 0. However, the proton needs to have a combined spin of +1/2. What this means is the final down quark has to have a spin of +1/2 in order to satisfy. This then gives the combined spin of the particle a value of 1/2. And as acknowledged earlier, up and down quarks all have a strange of 0, which satisfies the strange requirement as seen in our diagram here. So what about our neutron? Well, a neutron has a charge of 0. And if it's going to be built from up and down quarks, again, there's only one combination that achieves this. We're going to have to build a composite particle out of one up quark and two down quarks. Two lots of -1/3 charge plus a 2/3 charge gives us a charge of 0, just like our neutron. The solution for our spins is going to be similar to our solution for the protons. Again, if we have two down quarks, the only way to make the two satisfy the Pauli exclusion principle is to give one a spin of 1/2 and the other a spin of -1/2. And if we want our neutron to have a spin of 1/2, as is shown in our diagram, that's going to mean that the up quark has to have a spin of +1/2. Combining all of these together, we should get a total spin of 1/2. The other particles that feature in the particle zoo are also composite particles and can be constructed from quarks in very similar ways. The quarks which compose them need to have the certain combination of charge, spin, and strange to yield the totals which match with the properties of the composite particles themselves. It's important to note that at this stage, Gell-Mann recognized that his work essentially just used mathematics to fill in the conceptual gaps of our understanding of the particle model of matter. While he had no foundational understanding or proof to demonstrate that his explanation was in fact correct and physically true, he was only able to show that this theoretical process that he'd undertaken worked out mathematically. Now, there have been times in scientific history where essentially a solution and explanation was given because it mathematically worked. Is one in the past that has been successful, but just as much as successful predictions based on mathematics have worked in the past, other times it did not. And therefore, Gell-Mann did not feel confident that this explanation was, the be-all and end-all or anything like that. He just wasn't entirely sure at the time. So this brings us to work that happened in the late 60s and early 70s that started to provide evidence for neutrons and protons being composed of fundamental particles, essentially supporting the work of Gell-Mann. So there are a few experiments and findings to unpack in this particular part of the course. The one that I'm going to focus on in this video first and foremost is the scattering experiment which occurred at the Stanford Linear Accelerator Center, also known as SLAC. So this accelerator has quite a long linear track through which a particle can accelerate. It then gets deflected for many experiments into this building here. And this here is the inside of that building. From here, the particle is able to pass through into this detector. And the detector can be swiveled along this track to take readings of particles that move in all sorts of directions radially. So let's have a look at some of the schematics to get a better understanding of how this experiment works. The experiment that we're worried about at SLAC was a scattering experiment, and it worked really similarly to the Geiger-Marsden experiment. In this experiment, which was at a significantly larger scale, alpha particles were being fired into a gold metal foil. And Geiger and Marsden were able to analyze the deflection of the alpha particles as they passed through the foil. Some went straight through, some experienced a minor deflection, and some were knocked directly backwards. This led to the determination that atoms were not made of uniform material, but instead contained a small and very, very dense and tightly packed cluster of matter in the center called the nucleus. The SLAC experiment worked quite similarly. However, scientists who worked on the project were not able to observe the deflection based on fluorescence on a screen. Instead, they had to guide particles towards a detector and essentially analyze each part of the scattering pattern individually. This again was achieved by rotating the detector in the room. For particles which were scattered in the experiment, scientists wanted to be able to determine the momentum of the particle. They were able to achieve this by taking the beam of particles and deflecting with a magnetic field. If the detector was to pick up any of the particles, the particle itself would have to move through this curved track. The ability for this beam to take the perfect path depended on the size of the magnetic field. If the magnetic field was too weak, then the beam of particles would crash into the lower side of the detector. And if the magnetic field was too strong, it would make the particles curve upwards too much and crash into the top part of the track. If we were able to get the right balance of magnetic field to velocity and momentum, then the particles would again flow through the track and hit the detector at the end. As such, the angle of deflected particles as well as their momentum were able to be determined as the detector moved across the room. So in this experiment, we were looking to see scattering by firing electrons at liquid hydrogen, essentially liquid protons. And by analysing the particles which came out of the liquid hydrogen and looking at their scattering patterns as well as their momentum, we were able to analyse the interaction between the electrons and the proton. If the proton was composed uniformly, scientists predicted that the electron would collide with the proton elastically. However, if the proton was made of smaller components, the collisions between the electron and the parts of the proton would be inelastic. From this experiment, these were the graph of results. It also included a theoretical line for what elastic scattering would look like. The measured results, however, did not fit this trend even remotely closely. Instead, it reflected inelastic collisions, again suggesting the protons themselves consisted of smaller particles. While this supported Gell-Mann's theoretical work, it did not prove it conclusively because there was no information about the properties of these particles, for example, charge. However, there were other experiments during this time period that gave further evidence to Gell-Mann's ideas. In other similar experiments at SLAC, we also were able to determine that these particles inside the proton, generally speaking, were measured to have a spin of 1/2. This agrees with Gell-Mann's theoretical work. And at CERN, an apparatus called the Gargamel bubble chamber was used to conduct scattering experiments with what we call neutrinos. And these neutrinos struck the nucleons which existed inside the chamber. I'm going to talk about neutrinos a little bit later in this video. For the moment, all you need to know is that neutrinos are masses, but they are exceptionally small, smaller than an electron, and they have no charge. So these neutrinos, again, struck nucleons inside the Gargamel bubble chamber. They were able to conduct scattering experiments. And when we look at their results, they came to the conclusion that the nucleons had little particles inside them, which contain partial charges of positive 2/3 and negative 1/3. Again, supporting the work of Gell-Mann. So through these three experiments, we now had three very key conclusions, which again match with the work of Murray Gell-Mann from 1964. And that was that nucleons contain point particles, they weren't uniform, that these particles had half spins, and partial charges of either positive 2/3 or negative 1/3. These were later known to be the up and down quarks. And so while other particles that weren't just up and down quarks were yet to be discovered, it was assumed that the basic principles of Gell-Mann's work would apply for the other composite particles. And it was through this work that we started to see the beginnings and the building blocks of the Standard Model of Matter. And so the Standard Model of Matter is built under the foundational understanding that matter is built from fundamental particles. Some things that you'll see here will be fairly familiar to you. Things like up and down quarks, electrons, neutrinos, which we just talked about before. We've talked about muons previously when looking at evidence for special relativity. We've also looked at photons, they're fundamental particles in the Standard Model of Matter as well. Possibly you've heard of the Higgs boson. It's quite famous. We're not going to look at it in much detail at all in the scope of this course, but it is one that you may have heard of nonetheless. So for the remainder of this video, what I want to do is start to introduce a lot of the key concepts which underpin the Standard Model and its structures. And so while we don't need to become an expert in every little part, the bits that I introduce will help you to understand, again, the concept of the Standard Model more broadly. Within the Standard Model, there are lots of new terms to learn, and I'm going to be introducing quite a few of them along the way, but they will be summarized at the end, and I've got a nice table of definitions for you to be able to reference as well. So let's start with the quarks. In this diagram, they're colored in purple, and the quarks are the building blocks which make composite particles. So things like protons and neutrons, or particles which are similar to them. In this diagram, there are 2 rows of quarks, and each row contains quarks that have different charges. The top row has charge 2/3. The bottom row has charge -1/3. In green, we have the leptons, and these particles don't combine together and hold together to make more complex particles. They exist individually. Again, they come in 2 rows. The top row has a charge of -1, just like the electron, and the bottom row are chargeless particles. These are neutrinos. And as I introduced earlier, neutrinos are smaller in mass than an electron, and they are chargeless, which is implicit in the name neutrino. All of these particles, the quarks and the leptons, are referred to as fermions, and they all have half-integer spins. These spins can be positive or negative, and they can be bigger than half or -half as well. You'll also note that in this diagram there are 3 columns. They're referred to as generations. Within one row, as you progress through the generations, charge is the same, spin is still half-integer, but the key difference between them is going to be their mass. Mass increases through the generations. So that is one of our key differences between our up, charmed, and top quarks, for example. On the right-hand side, we have our bosons. These are particles with whole integer spins. For the particles shown in this diagram, they have spins of 0 and 1. But there are other bosons which don't fall into this cluster, these force carriers as they're shown here, that have spins that aren't just 0 and 1, but are whole integers including negative numbers. We'll get to some of them a little bit later. You'll notice that these bosons are split into like a red and an orangey yellow kind of color, gauge bosons, which are vector bosons, and scalar bosons. We're not going to be distinguishing between them really at all. What I want to emphasize, though, is what kind of force is carried by some of these bosons. So the gluon, while you probably haven't heard of it before, is one that you're going to want to start to wrap your head around a little bit, because it's probably the one that we're going to be learning about and talking about the most in the context of the Standard Model compared to the rest. The gluon mediates the strong force, which means that it actually holds the quarks together to form composite particles. We then also have the photon, which mediates electromagnetic force. You then also have the Z and W bosons, which mediate what we call the weak nuclear force. But this force isn't really within the scope of our syllabus, so we're not going to be spending much time on it at all. So while that first slide was a little bit to take in, turns out the Standard Model just gets that little bit more complex. Not only do we have all of our fundamental particles that we've just identified, but we also have what we call antiparticles, antiquarks, and antileptons. The difference between particles and their antiparticle counterpart is they have opposing charges. So their other properties are the same. Again, the only difference is that their charges are inverted. So for our up, charmed, and top quarks, which all have 2/3 charge, the anti-up, anti-charm, anti-top quarks all have a charge of -2/3. So if they belong in the top row, their charge is plus or minus 2/3. For down, strange, and bottom, which usually have a charge of -1/3, their antiparticles are positive. For a top row of leptons, they're usually -1 in charge, but again, their counterparts are positive. And for neutrinos, whether we're talking about a neutrino or an antineutrino, their charges will be 0. It's at this stage that I want to emphasize you do not need to become an expert in every single one of these particles, which you can see in this diagram. There are some that you want to get your head around a little bit more and be able to recognize key features of. And the others you can, for the most part, ignore. If you needed to apply your understanding of any of the others, that you'd be getting information in a question, etc. The ones that I want to be focusing on predominantly, though, are the up quark, the down quark, the electron, which we already know quite a lot about, the electron neutrino, the muon, the positron, also known as an anti-electron, and the electron antineutrino, or the positron neutrino. These are the quarks and leptons that will come up the most often within the context of our course and are the ones that you're going to be able to want to recall a fairly solid understanding of quite readily. For some of our force carriers, our bosons, the ones that are the most important in understanding are the gluon, because that's going to explain how we form composite particles, which I'm going to show you in a second anyway, and the photon, which, similar to the electron, is a particle that you're already fairly familiar with. So far within the standard model, we've identified that matter is built from fundamental particles, some of which are antiparticles. And when we form these composite particles, we form what we call a hadron. And these are held together by gluons. The gluons, again, are force mediator particles, which exist within, say, a proton, a neutron, or some other hadron. And they hold together the quarks that compose them. So in the diagram that's here on the left, each of these little bonding lines are actually representations of the gluons. An alternate diagram for a proton may look like this. So in this diagram, we have our 3 quarks, our 2 up and 1 down, being held together by 3 gluons, which exist in between each pair of quarks, and then a dotted line which represents, I guess, the boundary of the proton. Essentially, these particles can exist anywhere within the bounds, but do freely move about the space through which the proton occupies. Similar diagrams can be drawn for any of the particles shown here on this slide. So again, these composite particles built from multiple quarks are known as hadrons. If we have hadrons composed from 3 quarks, we call them baryons. As alluded to earlier in the video, baryons have half-integer spins, which makes sense because each quark has half-integer spins as well. And so if 2 are positive half and 1 is a negative half, you're going to end up with a spin combined at the end, which is 1/2. Mesons, on the other hand, are made from 2 quarks. They're always made from 1 quark and 1 antiquark. We won't get into the math today, we'll probably do it in class, but the reason why you need a quark and an antiquark is to ensure that you end up with integer values for charge. Another rule about mesons is that they always have integer values for spin. And this makes sense because they're always composed of 2 quarks, both of which have half spins, which means that the 2 half spins will either cancel out and become 0, or they'll combine together and become 1 or -1. So in introducing the standard model, we learnt about a whole bunch of different keywords. We learnt about fundamental particles first and foremost, and these included quarks and leptons. Quarks which can combine to form composite particles, and leptons which exist by themselves. The other fundamental particle is a force carrier particle which mediates fundamental forces, including the strong and weak force and the electromagnetic force. We then also started to talk about composite particles. Hadrons is the keyword that we use to describe a composite particle made from multiple quarks put together. We learnt that mesons were made from 2 quarks and baryons were made from 3 quarks. And there were 2 other terms that we came across as well, bosons and fermions. And these are groups of particles, whether they're fundamental or composite, which are based on the spins of those particles, whether they are integer spins or half-integer spins. What that means is some particles are fundamental, some are composite, some are bosons, some are fermions. You can't be a fundamental particle and a composite particle because you're either not made of smaller constituents or you're made from two or more fundamental particles. And similarly, you can't be a boson and a fermion. You can't have whole integer spin and half integer spin. And so what that means is we have particles which can either be classified as fundamental or composite, and boson or fermion. And there are different combinations of each. This can be best shown by using a Venn diagram. So bosons are particles with whole integer spin. Some of them are not hadrons. They are not composite particles. And these are our force carriers. This includes our gluons, our photons, our W and Z bosons, and our Higgs boson. There are also some bosons which are composite particles. These are mesons, and they always are made of two quarks. Fermions have half integer spin, and some particles have half integer spin and are not hadrons, not composite particles. These include quarks and leptons. Fermions, which are composite particles, are referred to as baryons, and they're composed of three quarks. While we went through a lot of new concepts and information today, I really do want to emphasize that you don't have to become an absolute expert in every aspect of what we covered. We're going to be revisiting a lot of these concepts in class so that you can consolidate and start to apply your knowledge, and that's going to be done with lots of guidance as well. So if you're feeling a little bit nervous, try not to stress too much. We'll sit in class and break down all of these concepts and make sure that we're all on the same page. Once we've done all of that, the next thing that we're going to start looking at are particle accelerators and how they work. We saw today that particle accelerators were some of the foundational apparatus which were used in order for us to start to build our understanding of the standard model. And as we started to get more evidence of parts of the standard model beyond what we looked at today, particle accelerators obviously still played a really important role in that. And so in the next video, we're going to look at how they actually work and how we are able to accelerate particles to smash things together to then see what happens. But until then, have a good one.